This is the lecture for linear regression. I'll show you how to get to all the materials you're going to need. Hopefully you can see the video this time and it's not just audio. So I'll go through it all again with video for people who want to see it. So you go to modules, then you scroll down to Baglioni, Chapter 9, Intro to Regression. In the Regression tab, here you'll see this thing that says Lecture Audio. You can just follow along with these PowerPoint slides in the lecture audio. You'll need each of these data sets. I've downloaded them to my computer before. This is R code that we're going to use. So when I click on that, it'll just open up RStudio for me. And then I'll get the lecture slides just to kind of walk through so you can see what's happening. Again, if you want to help, if things aren't working for you, it's really hard remotely to answer questions via email, like when you're like, hey, my R code's not working. It's a really hard thing to do. If you're in Rexburg, I strongly recommend that if you're struggling with this stuff, just schedule an appointment. We can sit down in my office. I can look at your code. Usually there's a simple answer, a simple solution to the problems you're dealing with. If you're not in Rexburg, sometimes I can talk you through it on the phone. Just remember, R's case sensitive, right? So one little thing wrong in your code and you're going to get error messages. So I know it's frustrating, but I promise that's how learning happens. You learn more as you make mistakes and struggle through stuff. That being said, I don't want you to quit class and have a difficult life and all that stuff. So let me know if I can help you. Okay, so what we're doing today is we're moving from description to prediction in terms of a relationship between two numeric variables. So there's this fun website I can show you, just because I like to show people fun websites sometimes. It's called Tyler Vegan. He just has this list of spurious correlations on his website. Right, so you can see suicides by hanging, strangling, and suffocation is strongly correlated with U.S. spending on science, space, and technology. You see over here, U.S. spending on technology, and here you have the number of suicides by hanging, strangulation, and suffocation. And you see that as this money goes up, so does the number of suicides by hanging and strangulation go up. So that there's a relationship there. The number of people who drowned by falling into a swimming pool, we have around, in 1999, we had around 110, it looks like, drownings from falling into a pool. And then you see here's the number of films Nicolas Cage appeared in. So in 2009, he was in 4 films, right? There seems to be a relationship. Okay, but what we're doing with regression is we don't want to know, is there a relationship between two variables? We want to know, if I know something about one variable, can I make a prediction about the other variable? Or if I know something about the number of people who drown by falling into swimming pools, can I predict how many cages or how many movies Nicolas Cage is going to appear in a given year? Something like that. So it's not just about the relationship, it's about prediction. So this is a common thing. Colleges want to know if your high school GPA is somehow associated with the GPA you get your first year in college. So that's a perfect opportunity for us to do linear regression. Here's a scatter plot of those two variables. This person got a 1.8, looks like, in high school, and then got a 2.0 in college, right? This person got a 4.0 in high school and a 3.6 in college, 3.5. So the question is, can we predict? If I know someone's high school GPA, can I predict their college GPA? The answer is yes. And the way that we do it is we just draw a line, a regression line. And then you can use the slope formula to make your prediction. So if I wanted somebody had a 2.3 in high school, I would just go up to this line and I would make a prediction that they would get about a 2.3 in college. Right? If somebody got a 3.0 in high school, then I would predict they'd get about a 2.8 in college. Just draw the line. Now you might say, that seems very simplistic and silly. And I will say to you, it doesn't matter. That's what we do in statistics. 80% of everything you see in published journals is based on drawing a line like this and making some prediction. So how do you know which line to draw? That's a formula that we use called ordinary least squares. Helps you decide the slope of the line. It's a simple formula. You could memorize it. I did in graduate school. I memorized it. They gave me data for a final exam. I had to remember the formula, then calculate the slope of this line, and then calculate the y-intercept, and then use that to make predictions. So you could do it too. If you're on like a desert island, all alone, trying to stay sane, rather than making a volleyball look like a person and talk to it, you could collect data. You could count the number of pieces of sand, and then you could count the number of leaves on trees, and you could see if you could predict the number of leaves in a section based on the grains of sand in that section. See? And then you could keep yourself smart and sane. So I'll explain how we derive the formula. Basically, if you look, my line never predicts any of these points accurately. In fact, we get it wrong every time. This is the closest we get to being right, and it's not exactly right. We don't care. This is still our best prediction because it's based on minimizing the distances between each of these points in the line. So in this case, the x was 3.3, and the actual y value is 3.7. So the difference between 3.7 and our prediction, which is like 2.9, we would call that error. We got this wrong because that person got a 3.3, and we predicted they'd get a 2.9, but really they got a 3.7. So 3.7 minus 2.9, we take that number and we call that error. And you do that for each of these points. The distance between each of these points and this prediction line, regression line, if you added them all up, it would actually be 0. So what we do is we square them, then we add them up, then we do some math, take the square root of that. And so that's why this regression line is called ordinary least squares regression. It's super, super common. It's been around since the 60s. The 60s is when they had enough computing power that they could do these things kind of regularly. They'd have a big computer set up in a whole building, and you'd take your data to them, and then they would calculate your regression coefficients, and you'd, like a week later, you'd go pick it up. And now in R, we'll do it in like a fraction of a second. But that's why people used ordinary least squares for so long. Computing power didn't allow them to do very much. Now computing power can do a whole lot more, and so there are people that get much fancier with statistics. But since a good majority of the people who've learned how to do statistics only ever learn how to do ordinary least squares, I get you to this point in the class because that's where a lot of people in the world are. And so if you can understand this and do this, you can do most of the statistics that most people are doing. So we are interested in minimizing the squared differences between each of those points in the line. Here's the formula. It'll probably look familiar to you from algebra, the y equals mx plus b slope of the line formula, only we change it around a little bit. So our predicted dependent variable, that's what this hat means, is it's our prediction. So our predicted y equals the intercept plus the slope times some value of an independent variable. Or y equals b plus mx. We're going to do a notation like this because eventually we're going to put in multiple independent variables, and they're all going to have their own slope. So you can remember this notation. So we can run this regression model in R. It's super simple. You got to give the regression model a name, so I always just call it mod.1 and then mod.2. Just keep things easy for me. You can call it whatever you want to call it. Mod.1 is going to equal, LM stands for linear model of freshman GPA predicted by high school GPA, and then the data set we're going to use is D1. So if I go over to RStudio, I have to read in this GPA data set. The GPA data set is not real. It's just made up data. So don't get too excited about what it might mean. So if I run that regression model and then I do a summary of the model, I get output that looks like this. So you see that the estimated intercept is 2.53. This is the estimated slope for high school GPA. We're going to just take the output a little bit at a time. And so eventually we'll learn how to interpret all of that stuff. But for now, we'll just focus on this to make sure you understand this part. So we're going to use this to make a prediction. If the high school GPA is 0, then we would go 2.53 plus 0 times this, which makes that 0. So then our estimated GPA for someone who got a 0.00 in high school would be 2.53. If they got a 1.00, it would be 2.53 times 1 plus 1 times this value. So it would be like 2.6 would be our prediction. All right, so we can practice that. If someone had a high school GPA of 2.8, it would be 2.53 plus the slope times 2.8. And you can put this right here, this equation, you can put this in Google. Google functions as a calculator. And you can see that if someone had a 2.8 in high school, we predict they'll get a 2.75 GPA in college. That's what that equation shows you. So now take some time, go ahead and pause this video and do this for yourself. What is the predicted GPA for a college freshman if their high school GPA was a 4.0, a 3.5, and a 3.2? Go ahead and pause it while you figure that out. You can use this R code if you want, because I put some R code in there to make it easy, right? That's our first prediction if you wanted to. Okay, go ahead and do it. Now I'm going to show you the answers. So if they had a 3.2 in high school, we'll just go to the Google and change this to 3.2. And they would get we predict a 2.78 in college. If they had a 3.5, we predict 2.81. And if they had a 4.0, 2.85. Right? Just go back to the Google and change this 3.2 to a 4, and then you get the answer. Okay, so now we're going to use the IQ data set. This is actually real data. It's kids' IQ scores and mothers' IQ scores. So in this data set, I'll just open it up real fast. I'm calling it D2, and the file name is called IQ. So when I open that, I can look at this data set and I see kid score, that's my dependent variable that I'm going to predict. Mom IQ, that's the independent variable I'm going to use to make my prediction. So I'm going to run that model there and then do the summary. So the slope of the line, I showed you how to find that. You can go ahead and look at my output if you want and see if you can find the slope of the line. And the answer is 0.61, right? Because it's this value, and then we round it up. That's the slope of the line for Mom IQ. And the intercept, right here, 25.82. That's the closest one right there. So it's the only one I rounded. It didn't go to 2 decimal places. Who cares? How good is our prediction? So that's the big question, right? This column here, standard error, tells you if you have a lot of error in your prediction for that. We want to do a hypothesis test and know if our predictor, our independent variable, is a significant predictor, or if there is a significant relationship between our high school GPA in this instance and freshman GPA. So what you do is you take the estimate, divide the standard error from that, which will give you the t statistic. You already know on a t statistic, the critical value is plus or minus 1.96. And then here's the p-value, 0.584. So this is less than 1.96. This is bigger than 0.05, no stars. So this is a not significant predictor. It's not a good one to use. We can look at the output from IQ, and we see that Mom IQ seems to be a significant predictor. I've got a t bigger than 1.96. I've got a p less than 0.05. I have more than 1 star, but 1 star is all you need. So I would reject the null on that one. I'm just going to change this so that it gets rid of the scientific notation, because some of you don't like scientific notation. Right, you see my p-value is less than 0.05. Okay. So now what we're going to do is we're going to use multiple regression, right? It's really unlikely that one variable is going to explain very much of the variation in your dependent variable. Like the mom's IQ might be a significant predictor of a kid's IQ, but what about the dad's IQ? And what about like if the kid has brain damage or something like that? So there's a lot of stuff that could go into explaining IQ. In multiple regression, we're trying to put in all of the stuff to see if we can figure out an explanation. So as you recall from your literature reviews that you did, where you talked about emotions and voter turnout, you found all this stuff about what predicts, what makes a person more likely to vote, right? Like older people, wealthier people, educated people, white people, they all tend to be more likely to vote. And then you hypothesized that maybe emotions would matter. Well, so statistically what you have to do is you have to put a model together that measures all that other stuff that matters, like education and age and maybe gender and maybe race and all that stuff from that literature. And then you add in emotions. So that's what I mean when I say your model should be based on theory. Your literature review tells you what independent variables you include in your model. So here's an example. We'll use actual baseball salary data. So this blue circle here represents a hypothetical, all the variation that exists in baseball salary. Maybe good players make more salary. Maybe the longer you're in baseball, the higher salary you'll earn. Maybe the team you play for matters, or maybe whether you're in the American League or the National League matters. So what we're trying to do in social science research is we're trying to, after we know all the stuff that everybody knows, you want to put all that stuff in your model and you want to find a new variable that explains new variation and doesn't explain any variation that's already been explained. So if your new variable is like this, where you basically explain stuff that individual attributes are, or let's say it's like this, right? You've got this new idea, but it explains the same variation as individual attributes, well, then your variable is not going to be significant. So in this case, one of these would be significant, but not both, because they explain basically the same variation. And what you really don't want to have happen is you have this brand new variable, and it explains all this stuff. And now this other thing that everybody knows is true is no longer significant. Because all these people will be mad at you and they'll be like, no, we already know that we're right, and they won't like your new idea. So that's I mean, in theory, it's a great thing, but in reality, it's hard to get that stuff published. All right, so what we want to do is we want to read in that salaries data set. So we'll call it D3, and I just think it's called salaries. Yep. So as you see in this data set, there's really just two numbers. There's the year, and then there's the salary. And you see for the 1985 Boston, this dude made 240 grand. And then you see like in Washington, they seem to be making more money in 2012. My guess is 480,000 is the minimum wage in that year, because lots of people are making that much. Anyhow, we want to know, do salaries go up over time? That's our question. Or is there a significant relationship between salary and the year? Or does year predict salary? So if I run the model, then there's my model. I do the summary, and I see, yes, here's my estimated intercept. It's enormous. Here's the year. It's positive. It's T is bigger than 1.96, and it's less than 0.00 for a p-value, and it has more than one star, so this is significant. So the way I interpret this is, as the year goes up by 1, the predicted salary in baseball goes up 130,333. Here I see R squared, 11.116. So this means that my model that has just this one variable explains 11.6% of the variation. So of all the variation in salary, the year that you play explains 11.6% of this. All right, so now we're going to add in another variable. We're going to add in if you're in the American League or in the National League and see if that matters. So we'll run this mod.2. And we look at that output. And we say, yes, league ID is significant. Year is still significant, or intercept, whatever, right? That's like if both of these variables were 0, so you're not playing in any league and you're playing in year 0, then that's your estimated salary. So it's just kind of meaningless. So it's significant, right? But it only improves our model by 0.05%. So if I leave this variable out, my R squared was 0.116 right there. Now I add this new variable in and it goes up to 0.1165. Now that's not 0. That's why it's significant, because it is explaining something, but it's not explaining much, right? If I were to put this back in my theoretical model here that I was showing here, league that you're in is actually only explaining 0.05%, right? This variable explains that much, probably about that much. It's not nothing. It's just not, I don't know. Just not 0. That's all that statistics tells you. There's not 0. Okay, so now I want you guys to, and it does explain more, right? 0.05% more. So it's not nothing. Okay, so now I want you guys to practice. I want you to predict kids' score by the mom's age, the mom's IQ, and the mom high school, and then tell me which of these are statistically significant variables. So go ahead and pause. I'm going to zoom in on this just to make it a little bit easier, because sometimes on the video, you can't see this stuff as well as you might like. So here's the output. Here's my inner, so here's the formula that you're supposed to use. Here's my estimate for each of these things. So which of these variables are significant? Here's a star, so mom high school, significant. Here's a star, so mom's IQ is significant. No star, mother's age then has no relationship with the kid's IQ score. My model explains 21% of the variation. You can use either the adjusted or the multiple, it doesn't matter. Multiple never goes down. If you put in a variable that's not a good predictor, it can't go down. So sometimes they adjust that and make it go down, right? Because this model has this variable, mom age, that doesn't contribute to the model. So this one sort of penalizes you. When I say interpret it, I don't care which one you pick. Pick whichever one you want. But if we're trying to explain all the variation in kids' score, my model with these variables explains about 21% of all that variation. So there's like 80% that we don't explain. But it's not 0. We're doing okay. And I can actually take that variable out because it doesn't help, right? So if I run this again, I get rid of mom age, the age of the mom, so, and run it again. You see how my R squared doesn't go down at all? This one does just a tiny, tiny bit. So basically, these two variables explain 21% of all the variation. So that's pretty good. Okay. Now I want you to add in, okay, well, let's interpret it. So a 1-unit increase in mother's IQ predicts a 0.56 increase in kids' IQ. And having a mom graduate from high school increases the kids' predicted IQ by about 6 points. So moms that didn't graduate from high school, their kids tended to have a little bit lower IQ. But since IQ goes from 0 to 200, this is actually stronger, right? because a 1 unit increase in IQ moves the kid's predicted IQ up by 0.5 point, a little bit more. So that's a pretty big effect. Okay. Let's add in whether or not the mom works outside the home, how many hours she works outside the home. Let's see if having a working mom hurts a kid's IQ score. So you run that model. Go ahead and pause it. Okay, so here's your output. So you tell me, is mom working outside the home a significant predictor of kids' IQ score? The answer is no, because my p-value is bigger than 0.05, no stars, t's less than 1.96. It's just like mom age, t's less than 1.96, p's less than or bigger than 0.05, no stars. So age, work don't matter. Look at my r squared, right? With just these two variables, my adjusted r squared was 0.214. Now it's 0.2077 because these are bad variables. That's what I was trying to tell you. My multiple stays just as high. So you can pick either one you want to interpret the model. So that's why I say, like, this model explains about 20% of the variation in a kid's IQ score. Given that IQ is genetically heritable, then it's good that the mom's IQ explains a lot of the variation. I would imagine all the stuff on the father side would too. I'll explain probably about 20% also, as much as the mom does. So then that gets us to about 40, maybe 50% if we put all the mom and all the dad things. Then that means the rest of it's other stuff that we don't know what it would be. Okay, so that's how R squared works. That's how regression works. Hopefully all this stuff makes sense to you. Let's just have a look at the homework real fast because I know that that matters to lots of you. Super easy stuff, right? I'm just having you predict something easy with made up data. These data aren't real. Predict ACT by IQ and high school GPA. Remember, when I say tell me about the explanatory power of your model, I'm asking you to interpret the R squared. If an independent variable is not significant, then the nature of the relationship is there's no relationship, right? But if it's positive, it means that when the independent variable goes up, the dependent variable goes down, or vice versa. And if it's a positive relationship, it means both of them move in the same direction. As high school GPA goes up, ACT goes up. As this goes down, that goes down. That's what it means. Okay, good luck to all of you. I hope you enjoy doing that as much as I've enjoyed recording this video for you.